Welcome to our final topic on physics. This one is topic H and it's entitled Stable Earth. And it's a bit of a mixture because the first half you would expect from the title, the second you might not, but it all gets thrown in the same one anyway. So far in this unit we've been talking a lot about waves, and we need to know about two different types of waves in order to be able to do the rest of this unit. So I'm just going to introduce a little bit of terminology to you and see if we can get our heads around these different types of wave. First type of wave we need is a transverse wave. Now transverse waves are where the displacement is at right angles to the direction of the wave. A picture might help here. So what you can see here is I've got a wave. Now the wave, if you look at the peak, it's travelling from left to right across the page like that. So that's the direction that the wave is going. But if we look at the individual dots which represent the particles, they are moving. If we just look at one, they're just moving up and down. So that's the displacement that we're talking about. So the displacement is up and down. I forgot which way around my arrows were going to appear then. So the displacement is up and down, but the direction that the wave is going is to the right. So those two arrows are perpendicular to each other, they're at right angles, and that makes it a transverse wave. The second type of wave we need to talk about is a longitudinal wave. So in a longitudinal wave, the displacement is parallel to the direction of the wave. So again, let's have a look at a picture. So with this one, we can see that the peaks of the wave are travelling to the right again. So if we just follow one along here, so this is a peak and it's travelling along. So the flow of the wave is sort of going to the right. Now if we look at the displacement, so if we just look at one individual particle, we can see, sorry, that's my chinchilla's getting a bit excited. We can see this one particle is moving from side to side here, and that is in the same plane as the direction that the wave is going. So the wave is going this way and the individual particles are vibrating this way. So our displacement is in the same plane, it's parallel to the direction that the wave is travelling. So that is a longitudinal wave. Right then, as you may have guessed from the title, this unit is related to the Earth. So we just need to know a couple of things about the structure of the Earth. We will go into these in a bit more detail when we get to chemistry 2, but for the time being, we'll just go through some quick basics. So on the outside of the Earth, we've got a thin crust of solid material, which is, depends where you are, but it varies from 10 to 100 kilometres thick. Beneath that, we've got the mantle. So the mantle, it acts as a solid, so for purposes of this unit, we'll consider it a solid, but it can flow, so it does move a bit. But as far as we're concerned on this unit, it's a solid. Then underneath the mantle, we've got the core. Now the outer layer of the core is molten, so it is liquid. And the inner portion is a solid again. But the important things for us is that we've got solid crust, solid mantle, liquid core, because that's going to matter when it comes to our next section. Okay, so we're looking at seismic waves right now. So seismic waves are just the name for earthquakes and how earthquakes travel. And they come in two different types. There are P waves, which stands for primary waves, so first, and that's because they get there first. These are the faster waves. Now primary waves are longitudinal, so they cause the ground to move up and down. They can pass through both solids and liquids, and they go faster through more dense materials because the particles are closer together, so they can move quicker. So if that's a house during an earthquake, if it's hit by a P wave, it goes up and down. Second type are S waves, which stands for secondary waves because they get there second, they travel slower than P waves. So these are transverse waves, so they cause the ground to move from right to left. They only pass through solids and they are slower than P waves. And they go faster through more dense materials as well, same as the P waves do. And they would cause the house to move from side to side instead of up and down. Okay. Right, so the reason we were looking at the Earth is because we need to figure out which waves can go through where. So if this is my site of an earthquake, and these are some earthquake seismic waves, we can see that these ones stop as soon as they hit the core. So they travel through the mantle, but then they stop when they hit the core. And if they follow this path, they can go all the way back up here and we'd feel them over here as well. But if they stop when they hit the core, it's because the core is liquid, so they can't pass through the core. So that means that they must be S waves, because they can't pass through the liquid core at all, they can only go through the solid. So if we look at some more waves that could come, so I've done these ones in yellow. These ones, they travel through the solid the same as the S waves did, but these ones here, they can keep going through the liquid core. They just they just change direction a bit. So it's just that they get refracted once they go through the liquid, and then they can carry on back through the other side. So those are P waves, because they can travel through the earth and they just get refracted when they pass through the different mediums, but they can go through both solid and liquid. And just as a note, these paths are curved, and it's just to do with the fact that the earth is different densities in different places, so it's kind of like constantly going through different mediums, so constantly being refracted. But this picture is one that the exam board quite like, so being able to sketch the path of these waves is very useful. Okay, so detecting earthquakes, we just use something called a seismograph. Then I'll show you some pictures in class, because there's a picture in your booklet. I couldn't quite manage to pull one together on paint for you, so we'll have a look at the one in class. But basically all they do is they just detect how the earth is moving. They use a pen and a piece of paper attached to generally a large ball that can move. It's hanging freely and it moves with the earth, and you can just see it just draws spikes when the earth's moving. But we'll have a look at one in class. Right, this is the bit where it suddenly flips and we start talking about UV radiation. I suppose it's because you get suntans on Earth, but there we go. So, getting a tan, what happens? Well, when your skin is exposed to ultraviolet light, it produces a chemical called melanin. And melanin is the chemical that causes your skin to be a darker colour. So when you get a tan, it's just that you've got more melanin in your skin. Now, people who have darker skin tones don't tan as easily because they already naturally have extra amounts of melanin in their skin. And what the melanin does is it filters out the UV, so it stops the UV getting further into your skin. It stops it penetrating further. It's basically protecting you from the UV. However, too much exposure to UV radiation can cause skin cancer. So the melanin is there to try and protect that from happening. It's not foolproof and it's not perfect, because too much UV radiation, regardless of your skin tone, can lead to skin cancer. So we all use sunscreen, hopefully, to protect ourselves when we go out in the sun. And it just increases the amount of time that you can be outside before the UV radiation damages your skin. And you can figure out how long it's safe to be out by using the formula below. Again, it'll be given to you in the exam if you need to use it. You just need to be aware of it. So the amount of safe time you can spend outside is equal to the time you could be outside if you weren't using sunscreen, multiplied by the SPF factor, so the sun protection factor of the sunscreen. So for instance, if it was safe to be outside for 1 hour before you burnt, and you put on factor 15 sunscreen, you could be out for 1 hour times 15, so you could be out for 15 hours. Now obviously that would be, a typical summer day in England where it's not very sunny. If you were somewhere near the equator, it might be that you could only be out for 10 minutes before you burnt, in which case factor 15 sunscreen is not going to last you all day. Okay, so linked to UV radiation is the ozone layer. You've got to be really careful with this. The ozone layer is what protects the Earth from excessive, so too much UV radiation. This has absolutely nothing to do with greenhouse gases or global warming. Totally separate. All we're interested in at the moment is the ozone layer, and that is linked to UV radiation. So, it was discovered in about the 1980s that there was a gap in the ozone layer above Antarctica, and it was somewhat unexpected. So if you have a look here, you can see the concentrations of the ozone layer, basically. So where the big blue bit is, this bit here, it means that we've got a hole, which is a bad thing. Don't really want that. The main reason that this is on the syllabus is because they want you to think about the scientific method. So, when scientists first found this out, not everyone believed it. It was a little bit controversial, so they had to do a lot more research into it, and they became more confident in their statement that there was a problem with the ozone layer because they did repeated measurements and they continued using new and better equipment, which is how they became more sure that there is this depletion in the ozone layer. And the next thing that also happened was that the results were repeated by other scientists. So repetition of results is what leads to certainty about whether or not something is really happening. So whenever they're asking you anything about the scientific method or about what's happening or how can we be sure that something is happening, the idea is that scientists repeat their measurements, that they can be repeated by different scientists, and they use that information to make predictions. And if the predictions come true, then what they've said is correct. Now, this is also linked into why, for instance, scientists publish information in journals. So they publish information in journals to show that what they've done, so that other people can repeat it, so that other people can check their findings, and that way it makes sure that everything that's being published as being true is checked. So we don't just take one person's word for things, because that leads to problems. I give you the MMR vaccine issues as a reason why we don't just believe one person, and we always make sure we check everything over and over and over again. So this is all about the scientific method, really, this stuff about the ozone layer. And these ideas could be applied to different situations, but that's the sort of thing that they were looking for. Okay, remember, if you've got any questions, write them down and ask me when you see me.